Hi everyone, welcome to another Friday's webinar of our QSUN group, Quantum Research Group of Stellenbosch University, and today's talk is about domain-driven application of quantum machine learning by Dr. Nouhaila Innan. Just a quick biography of Dr. Nouhaila. Dr. Nouhaila Innan is a research team lead at eBrain Lab division and is a postdoctoral associate at the Center for Quantum and Topological Systems (SAQuTS) at the New York University of Abu Dhabi, and she earned her PhD in machine learning from Hassan University of Casablanca, Morocco, if I'm not mistaken, where she also completed her bachelor's and master's in physics and neurotechnologies, specializing in material and nanomaterial. At the moment, her research focuses on quantum machine learning, quantum algorithm, and their application in fields like finance and healthcare. And she's passionate about mentoring and making quantum technologies accessible through global initiatives. And actually, we met 2 years ago in the NYU hackathon in Abu Dhabi, and we met again this year. So I said maybe it's interesting to initiate a collaboration between our group and your group in Abu Dhabi. Okay, please, floor is yours.
Thank you, Omid, for the invitation. Let me just share.
Yeah, you can see your slide.
Okay, great. So yeah, I will talk today about quantum machine learning and some application. So starting with what is quantum machine learning? So probably you are familiar with that, but like quantum machine learning is like a research area that explores the interplay of ideas and approaches, techniques from quantum computing and machine learning. And so it starts, of course, like with the qubits, which they are like the fundamental units of quantum information. And to manipulate these qubits, we are using quantum gates, which are like the operation that exploit like the quantum phenomena like superposition, interference, entanglement. Then from this quantum gate, we can have the quantum circuits, which are like the networks of quantum gates designed to perform a specific task. Then what's the difference between a quantum circuit and quantum machine learning model? So when we imply like this quantum circuit to perform a specific task in machine learning, like classification, prediction, regression, clustering, etc., and we use kind of like a trainable parameters in this circuit, this is when we are talking about quantum machine learning. How it works, it's just like classical machine learning. So first of all, we have classical data. We do like the pre-processing classically. Then after cleaning and making the data ready, we start like the first part of quantum machine learning, which is the data encoding. So we convert the classical data into a quantum state. And there is different techniques for that. Then we have the ansatz, or like the parameterized circuits. Here when we have like a sequence of different gates, and technically we use the parameterized one, like with parameters, which here like the angles, because we want to train them. Then of course like measurement. So here after like the processing the data through the quantum circuit, we measure the quantum system to extract like the output. And this measurements collapse like the quantum state into a classical values, which are then used for further analysis or decision making. It depends. Sometimes we use kind of like classical layers to help us like do this classification or decision making. Then of course we have a loop, which is iterative refinement. So this model undergoes iterative refinements where the parameters or like the parameters of the quantum gates are adjusted to minimize the cost function. And this iterative process continues until the model converges to an optimal solution. And this is like the key point. We have the scalability, speed, accuracy, and versatility. But the thing about this key metrics are, it's not always the case. We cannot generalize. It's like it depends. Maybe in a very specific scenario, in a very specific task with a specific data set, we can achieve those. Yeah. And this slide summarizes like the core component that forms the foundation of QML. So on the left side, we begin with the data encoding, as I mentioned, and there is like the important one, or like the most used one is like basis encoding, angle encoding, and amplitude encoding. And it depends on the problem. And basis encoding most of the time is like not really used to perform like specific task for the application side. So most of the time we are using either angle encoding or amplitude encoding. Amplitude encoding sometimes when we are dealing with like a lot, like a data set with a high number of features. So we use amplitude encoding because we can encode like square n of like the number of qubits. So if we have kind of like 16 features, we can use only 4 qubits. Then we have the ansatz. And there is like common choices like include real amplitudes, like key unitary pair circuits, and sometimes more expressive like the quantum tensor networks ansatz like MPS and MIR. And this circuit defines the variational space we explore during the optimization. And then based on this too, we have the models. So there is like QNNs, quantum graph neural networks, super vector machine, LSTM, physical neural networks, and quantum convolutional neural networks. So these models are tailored like to different types of input data and the learning task, either regression, classification, prediction. And on the right side, we highlight like the application where quantum machine learning show like strong promise. We have like climate modeling, material science, like predicting or calculating the ground state energy of such molecules, cybersecurity, transportation, where we optimize, like it can be travel salesman problem, for example, and the finance, there is market prediction, or like the fraud detection, healthcare. So these domains can benefit from the potential quantum advantage. Then finally, at the bottom here, we acknowledge that current challenges, this include algorithmic barriers like the barren plateaus, issues with like robustness under noise, lack of standard benchmarks, especially when it comes to comparing classical to quantum, and limitation due to the current hardware and data privacy constraints. So during this presentation, I will walk you through a few of this application in more details, starting with quantum state tomography. So quantum state tomography can be intuitively understood as a way of reconstructing a hidden 3D object using its 2D projections. So as you see here in the left side, so this is just like an analogy. The observed objects comprising like various shapes represent the complex quantum states. And through the tomography, we collect like projection from different angles and combine them to recover the internal structure. So in the quantum states or systems, we perform a series of measurements. It's like similar to these projections to infer the unknown state. And here on the right side, it illustrates the idea with real quantum data. So the first plot shows the reference or like the true quantum state. Then the initial guess is like what we start with, often just like a noise or a flat assumption. Then finally, through iterative reconstruction, we arrive at the final results, which closely approximate the reference. So this highlights the power of reconstruction, but also underscores the challenge. So usually achieving just as like accuracy traditionally requires like a vast number of measurements. So our motivation was like to explore quantum machine learning methods that can reconstruct this state more efficiently. And of course, like there is a lot of classical techniques that use that, but we focus on the quantum side. And since it was unexplored at that stage. So first, we started with this approach, which is like variational quantum circuit. So it's just like, as I explained, we encoded the classical data, which was like kind of like a quantum state into quantum states. It's just like it was a simple encoding because the data somehow was like in form of classical, but it represent the quantum states and it was available. So then the variational circuit is then applied to generate a candidate quantum state. And these parameters of the circuit are iteratively optimized to minimize a loss function defined as like 1 minus the fidelity between the predicted and the actual state. Importantly, so half of the qubits are used for representing the mixed target state, and the other half serves as like auxiliary qubits. And then the output is evaluated and the fidelity is computed using trace-based expression. And then one thing about this model or like this approach is the computational complexity. So here computational complexity refers how the required computational resources, just like it can be time or memory, scales with the size of the input. So in the context of quantum state tomography, the input size is typically characterized by the dimension d of the quantum state. Here, the VQC approach scales efficiently with the number of the qubits, which like represented with the dimension of the matrix of the quantum density matrix. Then moving to a second technique that we use in this work, so it's parameterized circuits for classical statistics, which is somehow very similar to the first one. So here, the aim is the same, is just like construct a pure quantum state by learning both its amplitude and the phase from the classical measurement data, which is different from the previous one. So specifically the frequencies of the outcomes over multiple poly bases. This was our data. To do this, we use like two parameterized quantum circuits for each reconstruction. So one circuit is trained to output the amplitudes and the other to output the phase of the quantum state. And together, they define the full complex coefficient in polar form, so the phase and the amplitude. Then the training objective is to minimize, like here we use the log likelihood loss between the observed frequencies and the model prediction using the Born rule. So we use it here to convert the quantum circuits output into probabilities. And it tells us like the likelihood of getting a certain measurement outcome by squaring like the amplitude of the corresponding quantum state components. So for each measurement basis, we compare like the predicted probabilities, like the one that are calculated using the Born rule, with the observed frequencies and update the circuit parameters accordingly. And in this study, we used two different circuits, A and B. And yeah, so here it's like they are like different from structure and the expressibility. So here we have like more entanglement comparing to this one, and here more parameters. And for like the computational complexity remains the same. And the thing that we need to highlight here is like the difference between this technique and the previous one, as they are somehow similar. So the variational quantum circuit learns directly from the quantum state and tries to approximate the full quantum state. Well, this use classical data, which is like the measurement frequencies, and fits into a quantum model to simulate the same statistical behavior. Moving to a third approach, which is Bayesian inference approach. So here we view the quantum state tomography as a problem of statistical inference. So we begin with a prior distribution over the parameters that define the quantum state. Then the measurements are performed on unknown states, and the outcomes are used to update our beliefs, forming posterior distribution. So sampling from the posterior allows us to estimate the most probable state as well as quantify the uncertainty. So this probabilistic view enhances robustness to noise and incomplete data, especially for our case, offering both fidelity and confidence in the reconstructed state. And for the computational complexity is also the same, but it also depends on the sampling strategies and prior model. And the last technique is quantum principal component analysis. So this is kind of like a powerful method for estimating the spectral properties of a quantum state, because it treats the density matrix not as a static object, but as kind of a generator of unitary evolution, enabling us to apply the transformation to another state. So using multiple copies of the density matrix and the swap operation, we simulate this evolution and apply quantum phase estimation to extract the eigenvectors as well as the eigenvalues efficiently. So this techniques excels when the density matrix is low rank, is as in many practical quantum tomography tasks, and allows us to reconstruct the state from its principal components. That's why it's called quantum principal components. To assess how well we approximate the original state, we compute the fidelity using the Ullmann formula. However, is that this technique, or the advantage of this technique, is most evident for the quantum native data. When applied to classical data sets, the speed up becomes kind of less significant due to input model limitation. Then for the computational complexity, so here offers one of the most favorable complexities, enabling efficient state reconstruction with reduced measurement overhead. Moving to the results, starting with the first technique. So our investigation focused on the relationship between the loss value and the two critical parameters, the depth and the number of iteration, as shown in these two figures. So starting with here, so this is the lowest low, the result demonstrate that the lowest loss and hence the highest fidelity was achieved at a circuit depth of 13. So here. And a clear trend emerged, increasing the circuit depth correlates with improved performance, suggesting that deeper circuits offer greater expressive capability for approximating quantum states, such as the ground state of a local spin Hamiltonian. And this algorithm achieves strong performance using a relatively small number of variational parameters and iterations. So the convergence you can see is from around 40. Moving to the second technique. So here we use the parameterized circuits for classical statistics with applied to 3-qubit systems using two different circuits, as I explained, A and B. So starting with the left side. So here we observe how average fidelity evolves with increasing the circuit depth. And fidelity here quantifies how accurately the reconstructed quantum state match the original target state. And a higher fidelity implies a more precise state estimation. And we see that both circuits benefit from deeper architecture but somehow circuit B is like consistently achieve slightly higher fidelity, especially at mid-range depths, indicating it might be better suited for capturing the underlying structure of the quantum state. Here on the right is like, it provides like insight by showing the standard deviation in the fidelity across repeated runs. So this matrix tells us about the consistency and stability of the circuit's performance. Here again, circuits B demonstrate lower variance across most depths, suggesting not only higher accuracy, but also more reliable behavior in practice. And with this result, it's highlighted that the circuit B is not only more expressive because it has more parameters, but achieves like better fidelity, also more robust, maintaining stable outcomes across trials. Moving to the Bayesian inference. So here we evaluated the performance of this approach. The posterior distribution was derived using likelihood and evidence functions. And of course, like the parameter optimization, here we use, I think, Nouhaila optimizer. So in the left side, it shows the posterior distribution over like the parameter theta for a 4-qubit system. And we use like the depth eight layers. So this posterior beliefs are formed after the sampling process and subsequently used to generate the new prior distribution, reflecting the adaptive nature of like the Bayesian methods. We then evaluated the model predictive capability by computing the fidelities and over like 25 randomly selected quantum states. So yeah, well on the right, we can visualize this fidelities. So each dot corresponds to a single state fidelity, with the green dashed line marking like the average. So these results demonstrate reasonable performance with variation across samples, suggesting that fine-tuning of parameters and possible reduction in circuit depth might enhance the stability and the accuracy, which means like fidelity in this case. Moving to the final method, we applied the quantum principle component. So here using 2-qubit setup, we begin with a known randomly generated state, then we applied the quantum phases summation using the 2 auxiliary qubits to reconstruct it. So for each parameter t, we run around like 50 independent quantum phase estimation iteration, and we calculated the fidelity between the original and the reconstructed state. So here you can see that the average fidelity across those like 50 runs exhibits like periodic behavior and reach its peaks around like the 20, achieving a maximum average fidelity of approximation maybe in 98%. On the right side, the plot shows the corresponding standard deviation of these fidelities for each t, reflecting how consistently the model performs. And of course, at the same optimal t, we observe not only high fidelity, but also reasonably low variation, yielding to a 50, not 50, but 95 confidence interval between these two. So here, this results confirm that this algorithm, when paired with like the phases summation, is capable of producing highly accurate reconstruction if the parameter t is appropriately selected. Moving to another application, which is cybersecurity. So cybersecurity has become one of the most pressing issues in our digital age and to illustrate the gravity of this situation. So some facts is like there were like more than 2,365 reported cyber attacks impacting like more than 400 million individuals. So, and there is like data breach and different type of attacks. So these numbers highlight the severity of the problem we are dealing with. So cybersecurity threats are not only increasing in frequency, but also evolving and making them harder to detect and neutralize. So given these pressing issues, working on cybersecurity offers significant benefits, of course, like effective cybersecurity strategies and enable precise risk management. But of course, there is like different type of like how to solve the problem. Of course, either by providing more robust quantum algorithms or quantum machine learning models, or maybe adding like more defense mechanism. But here it's slightly different because we are exploring whether like quantum machine learning can address or at least mitigate this issue in a different way. Because we are using the clustering to cluster the severity of these different attacks based on a data set. So here, this is the methodology that we used. So focusing on two quantum enhanced k-means clustering algorithm. We have the Q-kernel and QC swap. So the first of all, we start with the data set, which is like very famous. It has like different attacks with different provider. And what we are trying to do is cluster these attacks. Then, of course, we perform labeling coding, sample imputation, and scaling issue using standard scalar and min-max scalar techniques. This ensures that our data is properly normalized, then ready for clustering. And after pre-processing, we initialize like the SON traits of for the clustering algorithms, and we explore different methods, starting with like spectral clustering. This is classical method. Then usually this spectral clustering, it involves computing the similarity and Laplacian matrix, followed by like a eigen decomposition. This leads to k-means clustering on the eigenvectors with cluster assignments based on the Euclidean distance. The focus of our methodology, of course, is like on the quantum approach. So we have two, and both methods involves quantum data encoding, where the classical data is encoded. Sorry. Then, yeah, these quantum states are then processed to assign the clusters. And this QC swap means the cluster assignments are based on the C-swap tests. So it's like a quantum specific method, while in the Q-kernel, the assignments are determined using a quantum kernel, which measure like the similarity between the quantum states. And both algorithms iteratively update the centroids and the cluster assignment until they converge, similar to the classical k-means. However, so this quantum approach offers significant performance improvement. And we evaluate this improvement using performance metrics such like silhouettes and Davis-Bouldin and other metrics for clustering. Okay, yeah. Then, yeah, in this step, this is very important because we need to find like how many clusters we want to do based on. This is called like elbow method. It determines like optimal clusters by plotting the WCSS versus like the number of clusters and see which one is kind of like better. So here, since like before getting lower. So we focus on getting like 4 clusters. And after trying like with 4 clusters, we need to define how we can explain these 4 clusters. This is what we did here. So this is like present the clustering outcomes using the 4 techniques. So the clusters are visualized in a 2D space with like the vendor, project, and the x-axis, and the product on the y-axis. And this, like the X markers indicate the centroids of each clusters. Starting with key means and the spectral clustering. So we observe a clear but relatively border separation of the clusters. So you can see it's easy to understand like the clusters or make the difference between these clusters. But they produce clusters that are less compact and more disparate, like comparing to the quantum ones. C in D. So here, this methods is like they take advantage of like the quantum approach that we are using and leads to an enhanced separation between the clusters, indicating better defined groups of vulnerabilities. So the most important part, how we can explain these clusters. So for example, the the first cluster is concentrated on critical vulnerabilities related to Microsoft products, highlighting areas of high risk. So anything related to Microsoft, this is the first cluster. Then the second cluster regroup medium severity vulnerabilities from a diverse range of enterprise software vendors and network solutions. So it comes like from vendors of like different software, and somehow it has a medium severity comparing to the others. Then we have the third cluster. It focuses on high severity vulnerabilities affecting products from Adobe, Cisco, and Google, indicating significant risk associated with this product. Then the last one, it's comprised like the vulnerabilities with high to medium severity, particularly from Microsoft and Oracle products. And somehow this is based on the results we had like to analyze them and try to figure out like how to explain and what does this clusters means. But yeah, it makes sense comparing to the existing literature. So the strategic implication of this finding are significant because like quantum clustering provides better defined clusters and also reveals the strategic areas of concerns. So by identifying and grouping these vulnerabilities more precisely, organization can prioritize like their cybersecurity efforts effectively, particularly in areas where like the vulnerabilities are concentrated. Moving to the results, so this is the performance metrics for different clustering algorithms. So we use like 3 different metrics. Silhouette, it measures how similar an object is to its own cluster comparing to the other clusters. Means like that, for example, that data point, is it like more to this more fitting with to this cluster or to the other cluster? And the higher silhouette score indicates better defined and well-separated clusters. And we have DB evaluates the average similarity ratio of each cluster with its most similar cluster. And the lower DB index is better, indicating more distinct clusters. Then we have CH. It assesses the ratio of the sum of between clusters dispersion to within cluster dispersion. So a higher CS like index suggests more compact and well-separated clusters. And from this results, so starting with QC swap means achieved like the highest silhouette score and the best DB index, reflecting well-defined and separated clusters. It also performed strongly in the CH index, indicating robust clustering performance. Moving to quantum kernel means, he also delivered competitive results matching like QC swap in the silhouette score and slightly outperforming in the CH index. K-means, this is classical, showed like a lower silhouette score and a higher dB, indicating less optimal cluster formation compared to the quantum approaches, save for spectral clustering. In summary, the quantum enhanced methods, particularly like QC swap, K-means, outperform like this classical approach across all evaluated metrics, but this is for just this specific scenario and with this data set. Moving to another application, which is climate modeling. So as artificial intelligence continues to evolve rapidly, so one of the major concerns we face is the rising energy demands in AI. And since 2012, energy consumption associated with AI technologies has been increasing exponentially, and doubling approximately every 3.4 months. This leads to significant challenge, not just like from a technological standpoint, but also with profound environmental impacts. So to counter this issue, the concept of green AI has like emerged. It emphasized the development of energy efficient algorithms and sustainable models that can reduce energy consumption. However, achieving true efficiency is more complex, like the Jevons paradox highlight like a crucial challenge. Making systems more efficient can sometimes lead to even greater energy use because of the expanded application and uses. And this is what we do, for example, even in quantum. Sometimes like to get like higher performance or better performance, we use like more depth and more resources. So it's not always the case if we want to use like sort of an algorithm to achieve efficient performance, but with lower energy or lower computational resources. So here we explored like quantum machine learning. How can quantum machine learning might provide a promising solution to balance the AI advancement with the sustainability, and using climate modeling as an application. So we use like the equipoise models, which stands like for adaptive quantum physics informed neural networks. So this model uniquely integrates like quantum computing techniques with physics informed neural networks, targeting applications in climate modeling. So the primary goal is to improve the predictive accuracy in the fluid dynamics, will of course significantly reduce the computational costs and the associated carbon footprint, to say that we are somehow using less energy. So we use the data set. It was derived like from the numerical solution to the incompressible Navier-Stokes equations. So this solution provides us with essential data such as like spatial coordinates, velocity fields, time points, and pressure fields. And we optimize data efficiency by flattening and reorganizing it, like selecting 30,000 key data points for training while utilizing the entire spatial grid for testing. Some key features of this method that we are proposing is like we are using quantum multi-head self-attention mechanism, which enhance the model performance. We are also employing like the quantum tensor networks to increase the representational capacity. And yeah, our model achieves somehow better reduction in the parameters, means like better carbon reduction, footprint reduction. Okay. Yeah, and this is an overview of our architecture. So at its core, our model used the physics-informed neural networks with embedded physical laws expressed as partial differential equations, or like what we call the PDE, directly into the learning framework. So this integration allows us to address both like the forward and the inverse problems effectively. And of course, like as I mentioned, one of the key innovation is the quantum multi-head self-attention. So this module encodes the classical data into quantum states and also computes the attention scores, aggregate them through tensor networks, enhancing the model representational capabilities. Our loss is like a function is like an hybrid one because it combines the data-driven loss, specifically like mean square error, with a physics driven component, ensuring that the output adheres to the governing physical equations. Finally, we use the optimization method as a quasi-Newton approach, which is further refined using the super conversions technique to ensure efficient and rapid training conversions. And this is the result that we got. Like our model achieved like a significant parameter reduction compared to the classical models, which was very similar, just instead of having the quantum layers, we have the classical. Specifically different quantum variation also, because like we use different ansatz of like the quantum tensor networks, demonstrated reduction as high as like 63.29. And for the test loss comparison, still our model delivered like comparable or even superior test loss relative to the classical enhanced pins. Then, yeah, our impact on the climate modeling, which is the application, is noteworthy by reducing like the computational demands, minimize like the carbon emissions, making the model highly sustainable for the environmental application. And yeah, on the right side here, you can see visual prediction for the current flow and the corresponding residuals. These plots highlight like the precision and the effectiveness of the model, capturing like complex flow dynamics accurately while reducing the computational overhead. Then moving to the last application, which is like resource allocations for 5G networks. So in 5G networks, one of the core challenges is like efficient resource allocation, specifically how dynamically assign like limited resources like bandwidth, like transmission power and frequency spectrum to a large number of users and service that have different and rapidly changing quality of service requirements. And somehow these resources must be distributed in a way that satisfies constraints like such low latency or like balancing the energy efficiency and fairness among the users. And of course, like there is a lot of classical methods that are solving this resource allocation, but it takes like a lot of computational complexity, especially if we are talking about large scale scenarios. And the other thing is like it has some difficulties in modeling the non-linear and high-dimensional interaction between the network parameters. So our motivation is to explore the quantum machine learning. Specifically, we are using variational quantum regression to see how it will be or how to use to optimize the resource allocation strategies. So yes, this is our method. So we use like this variational quantum regression, which maps like classical 5G networks parameters to optimal resource allocation values. So the task is regression, which is somehow different from the other tasks. So it refers to learning a continuous relationship between the input features. And here we have user density, signal strength, and bandwidth demands, and a target output, like optimal resource allocation. And usually, like traditional regression models estimate the coefficient for each feature. In our case, these coefficients are learned as parameter in a quantum circuit. And it's like any quantum machine learning, as I explained in the beginning. So it starts with data encoding. Here we use like Z feature map, which is like a pre-built function from Qiskit. It's use like the Hadamard and phase gate, which are like part of the angle encoding. This is to allow us, or to allow the circuit to represent the nonlinear patterns by modulating like the quantum phase. Then we have like the ansatz, which is real amplitude ansatz, also pre-built function from Qiskit. It consists like from parameterized rotation and entangling CNOT gates that explores the parameter space. Yeah, so this hybrid quantum classical structure enables us to perform regression in a high dimensional space, capturing complex relationship between like the network load and traffic conditions, and of course, optimal resource allocation strategies. And this is our methodology, or like the algorithm. So we begin by selecting the most relevant features, followed by like a standard train test splitting. Then yeah, the idea here, or like the core idea here, is to identify the optimal circuit depth. And we try like with the different number of layers that I will show in the results. And we loop through multiple depths by training the VQR model and computing the mean square error after each run. And the configuration with the lowest MSE is retrained. Then once the best steps is determined, we retrain the model and evaluate it using the classical regression metrics. Specifically, we use like MSE error, MSE, and mean absolute error. This matrix helps quantify how accurately the quantum model predicts the resource allocation. Yeah, and this is the result. So on the left side, we analyze like 8 different circuit configuration, each with an increasing depth layer. So here it shows that the depth 7 achieves like the lowest objective function value, suggesting it provides the best balance between the model expressivity and trainability. Well, on the right, it's just like the convergence behavior using the optimal depth. The objective function, as you see, rapidly decrease, and stabilize around the 125 iteration, indicating that the optimizer effectively located a well-performing parameter region for the 5G resource allocation. And yeah, this is a scatter plot comparing the predicted values with actual allocation. So the data points closely follow the red diagonal line, which indicates kind of like correct predictions. And this alignment confirms that the model is learning meaningful relationship between the network features and the allocation outcomes. However, we have the minor deviation still exists, as you see here in the top. And somehow, like, still, like, we need to enhance the algorithm more to make sure that we don't have those. But this might reflect just like an kind of like underrepresented samples or local non-linearities not fully captured by the model. Then on the right side, we analyze the residuals, the difference between the actual and predicted values. So the histogram overlaid with a smooth density curve shows the most prediction errors are small and cluster around 0, which is desirable. However, the leftward skew indicates that a slight underestimation bias. So in practical terms, this means that the model tends to allocate slightly less resource than required in some scenarios. This is a useful diagnostic as it can guide further tuning and rebalancing the training data or adjusting the circuit depth. So yeah, and together with this plot, it validates the model overall strength well, also pointing to precise areas for refinement. And yeah, to conclude, so during this presentation, I explored like a different set of quantum machine learning techniques tailored for different real-world challenges. We started with the quantum state tomography, where methods like VQC, Bayesian inference, and QPCE demonstrated varying trade-offs in fidelity and efficiency, showing that quantum machine learning-based strategies can reconstruct quantum states with high accuracy. In the context of climate modeling, we introduced our model, which was a hybrid quantum classical model integrating quantum attention into physics-informed neural networks. And the model achieved a significant reduction in parameter count without sacrificing the performance, pointing towards like a more sustainable approach for complex physical simulation. Turning to the cybersecurity, we proposed the quantum enhanced clustering framework that somehow surpassed like the classical methods, but still we cannot generalize that in enabling more strategic traits, prioritizing using a real data set. We also demonstrated how variational quantum regression can be applied to optimize the resource allocation in 5G networks. And the results showed like low prediction errors and also smooth convergence behavior across different circuit depths. Overall, this kind of contribution underlined the versatility of the quantum machine learning and its promise across this kind of application, ranging like from the environmental modeling to network optimization and digital security. Looking ahead, of course, like future research should continue to address the scalability, quantum circuit optimization, and the development of meaningful metrics to assess the robustness and interpretability in applied quantum machine learning. And lastly, yes, comparing classical to quantum, it's important, but we need like for that to define the metrics first. And yes, and before I conclude, I'm excited to share that we are organizing like a workshop as part of deep learning in Dhaba, QML for Africa workshop, which will take place in Kigali, Rwanda on August 22. So this workshop will bring together like researchers, students, anyone is like interested or working on quantum machine learning and quantum computing across the African continent. So everyone is welcome to participate and scan the QR code to learn more about this. And yes, and thank you for your attention.
Okay, thank you so much for your interesting talk. Now we have time for questions in person and online. You have a question on? There was a question in the chat. Okay. Yeah.
So yeah, I can read that. How does it basically differ from classical model like artificial neural network? I'm not sure like which model we are talking about, but in general, quantum machine learning is somehow very similar to what we are doing in classical. Just instead of having, for example, first the quantum circuit instead of the neurons and the classical layers. So we have what else that can be done? So yeah, so instead of bits, we are using qubits. This is not a proper uh, comparison, but somehow this qubit has like more, or like they have some quantum physics properties that they are not in the classical. Yeah. I think all the quantum phenomena, that's the difference. And of course, like from the performance, that's what are like everyone in quantum machine learning is trying to explore, which we call like potential advantage. How is it better than the classical? Or even the question is like, can we compare them? So, but somehow it's very similar to the classical because we are using to evaluate the models, we are using the classical metrics that comes from the machine community. I hope that answered the question.
You have another question. Yeah,
Hello, thanks for the talk. Can you just comment on how you find the centroids by doing spectral clustering? Exactly, how does that work? Because you plotted them in those figures of yours. How do you actually calculate the centroids for spectral clustering?
Yes, so regarding that, this is what we call like the quantum architecture search. So it's very hard because like we are kind of dealing with a black box, and even sometimes you start like with dealing with the equation to represent what you want to do exactly, but somehow once you start performing or like doing the experiments, it doesn't lead to what you want exactly. So somehow at some point you keep just trying and narrow down the search. So that's what right now almost like all the people are focusing on, having such of like an automatic tools that do design or search for the best architecture automatically instead of doing it like manually. So you give, for example, you give the metric that you want. I want a circuit that has like a performance of 90% accuracy. So either you give like all the pre-built insights or like the quantum circuits that are already available, or somehow you try to construct your own. You give like, for example, I have this gate. So based on this gate, you can generate random circuits, and based on that you keep testing until you find your like the best one. But of course there is the technique which we call like trainability and expressibility. So it means that somehow when you make your circuits more expressible, and you need to add more layers, more entanglement, and there is some studies going on that, like what actually adds more to the more expressible. So once you have that, it means that like more expressible means that you have more the space solution is like more covered, and it's easy to find your solution. But how is it, or how it in fact affects like the performance? That's also a kind of open question. So technically, there is no specific answer. So you know a couple of techniques, and you have, of course, like the literature, different existing works, and based on that, you customize. Either you start by using pre-built one and customize based on the performance that you are getting.
Okay.
Yeah, and I can add one thing more is like right now there is like some groups, so like they are working on adding kind of like a data set of the circuits. So for example, we don't have to worry about like uh, designing the circuits because we have a data set of different circuits, and we just need to uh, search for the best circuits based on whatever available in this data set. This is also one of the techniques.
Okay. Any other question here? Well, or not? Okay, or online. I don't see any other question, and it's 3 p.m. should be session. Thank you so much again, Nouhaila, for your interesting talk. This talk will be hopefully will be available soon on your YouTube.
Yeah, I hope so.
I hope so. Okay, thank you so much, and have a great day. Okay, thanks.
Thank you.
Thank you.
Bye-bye.